So here in chapter 1, we started with a little bit of idea about the atom and really sort of matter itself. So we talked about the different sort of states of matter. We talked about solid, obviously liquid and gas. We also talked about the transitions that go between these different states of matter. Again, solid to liquid, that is our melting. Liquid to solid, that's our freezing. Liquid to gas, our evaporation. Gas to liquid, our condensation. Solid directly to gas, sublimation. And gas directly to solid, deposition. We also talked a little bit about the idea of energy. And again, we don't talk extremely a lot about energy or specifically about energy in this sort of semester, but it does pop up a lot, obviously, in other chapters that we will cover. Again, really the basic sort of things to keep in mind as we go through the different chapters and sort of relating to energy. A lot of times we will see it in the form of delta H, which is the enthalpy, or the change in enthalpy. And that's sort of the heat of a reaction. And for the most part, if a reaction is endothermic, which means that heat and energy is going to be absorbed we typically will see delta H values being positive numbers. And in general, energy values that are positive usually implies that that's an endothermic type process. And that's opposite of a exothermic process, which is really sort of the other process that could occur in terms of energy. And that's when heat and energy is released. And in exothermic type processes, energy values are negative. So typically a negative value for energy, be it delta H, Q, whatever it may be, or just a change in energy, internal energy. They're negative. Usually that implies an exothermic. Somebody is basically releasing a certain amount of energy and somebody is gaining a certain amount of energy along the way. We finished up talking a little bit about scientific method and the idea of, it starts with observations. And we also have obviously a hypothesis as a tentative explanation of what you observe, something that can be tested. Then you obviously do the test through experimentation, obviously leading to more observations, perhaps a vicious circle of more experimentations and things like that. Again, eventually perhaps leading to, as we talked about, really a law or either a theory. And really kind of the major difference between those two, a theory, again, is something that may not hold true in all situations, may be revised or found maybe not to be correct in all aspects over time through further experimentation, while a law is really something that occurs, pretty much always the same way. It doesn't really change and things of that nature. Any questions on anything we talked about there last time? Okay, then we're going to sort of roll in now into really the idea of eventually here the atom, and sort of we'll talk about some experiments and some things that led to the understanding of the structure of an atom. Remember that the atom is the basic building blocks basically of all elements. It's their basic representation. So Greeks were the first to sort of explain why chemical changes occurs. Robert Boyle, Boyle's law in the gases, thank you, is thought to be the first sort of chemist, performed a lot of quantitative experiments. Quantitative experiments are obviously, quantitative is measurements, right? Experimentation. Qualitative is more observations. Two important laws sort of came up. There's the law of conservation of mass. So mass is neither created nor destroyed. So as we touched upon a little bit yesterday, when we have a chemical reaction, because really the only thing that happens is we're really breaking bonds and electrons are involved, we do have a conservation really of the elements. So we do have a conservation of mass. So that means however much mass you start with should be what you end with. Again, if you have those, like say 4 carbons like we talked about last time, and your reactants and your starting material, you will still end up with 4 carbons at the end of the experiment. which means, again, the mass of those carbons are going to be the same. You're not going to lose them. They may be in some different type of compound along the way. The law of definite proportions, a given compound always contains the exact proportion of elements by mass. So for example, if we had H2O, that's basically 2 hydrogens for every 1 oxygen that's there. We basically have 1 oxygen that's like 16 grams. We have basically 2 hydrogens, which is about 2 grams. So it's essentially roughly 1 gram of hydrogen for every 8 grams of oxygen in water is basically always a proportion of water that you get. Those being the molar masses of each of those elements is where those 16 and sort of 2 times 1.008 comes from. So no matter where you get your water, you'll always have that same percentage or ratio of the mass of each of those elements in there for a particular compound. It doesn't change. Atoms come together, in proportions that basically allow them to keep those same sort of ratios that you have there. If you had something like N2H4, that's basically 28 grams of nitrogen for 4 grams of hydrogen. Again, nitrogen is about 14.01 grams per mole. So obviously, if you take 28 divided by 4 there, we'll get 7. And that's basically 7 grams of nitrogen for every 1 gram of hydrogen. If you had something that was, say, NH2, that is again going to be 14 grams of nitrogen for every 2 grams of hydrogen, which once again is also 1 gram of hydrogen for every about 7 grams of nitrogen. So everybody comes together in terms of their ratios and these definite proportions of ratios. Also, why when things come together, we always have whole atoms, right? We don't have kappa atoms or anything like that when they come together. That also is something that Dalton sort of talked about, the law of multiple proportions. When 2 elements form a series of compounds, the ratio of those masses of the second one to the 1 gram of the first one is always reduced to the small whole numbers. That's sort of what I just showed you there on the last slide as well. But essentially, when atoms come together, they come together in the simplest way to basically allow them to be really stable. We'll talk a little bit about it as well when we get to bonding, but they do come together in the simplest way to allow them to, in a case of, say, bonding, reach sort of noble gas configuration, which are noble gases there on group 8 of the periodic table. And they do that in the simplest way. Ionic compounds are like that as well. You just need 1 sodium, for example, with 1 chlorine to make sodium chloride, but you need 1 calcium, and you would need 2 chlorines to make that all work out as that when they come together. So always the simplest way that they come together, and they always maintain those proportions, really kind of like what I just showed here on the last one. Wherever that slide went, there it is. These are both really nitrogens and hydrogens, and you can see in the end they come together in the same sort of proportion in terms of masses of each of those guys. So let's talk a little bit about Dalton. So Dalton, come back. So the first sort of real sort of theory about the atoms came from Dalton, and this is John Dalton here. His name kind of went up there in the other area there. So he was not a great lecturer. He basically wrote down the weather every day of his life. He never married, but he did like to go bowling on Thursdays, which is a really important thing to know for this class. So that definitely will show up on the exam. Remember, don't pick any other day, should be Thursdays. But really what he's known for is the precise definition of what we call atoms. And I'm not joking by that. That really will show up, just so you know. All right. So Dalton's atomic theory, there's several parts to Dalton's atomic theory. So let's talk about the main parts of it. He said that each element is made up of these tiny particles that he called atoms. He thought that atoms were sort of this idea at this point that they were indestructible. The idea that atoms are indestructible is not so correct. The idea of sort of nuclear reactions, and you can basically change one atom of an element to something else, is can occur in a nuclear reaction and not necessarily a chemical reaction. So that's not so correct all the time here. He also said that atoms of a given element are identical. The atoms of different elements are different in some fundamental way or ways. This also, again, is a Dalton's atomic theory. So as we talked about, it was sort of later proven that not all aspects of his theory are correct. And this is another one that is not necessarily correct in all aspects of it. The atoms of given elements are identical. The existence of isotopes, as we will talk about, which are basically the same element, but they have different masses, basically disproves that. So not every, say, nitrogen atom or every fluorine atom is exactly the same as there's existence of isotopes, even though they are still, fluorine, nitrogen, or even hydrogen, for example. But the other part of it's okay that, atoms of one element are different than atoms of another, but you can have isotopes which are the same element and still have some differences there. So again, that's another aspect of his atomic theory that's not correct. He said that chemical compounds are formed when atoms of different elements combine with one another. So that was sort of the definition we talked about the other day as well, that again, if you have a compound, it is two or more atoms of different elements together. And again, that differs from the generic definition of a molecule, which is just simply you need two or more atoms. They could be the same element or different elements as well. A given compound always has the same relative numbers and types of atoms as well. So if you have something like water, it will always have those two hydrogens to one oxygen. If you've got something like sodium chloride, it will have that one sodium to one chlorine sort of relationship that is there. He also said that chemical reactions involve really the rearrangement of the atoms, changes in the way they are bound together. And that really is sort of what happens in a chemical reaction. In a chemical reaction, what we start with are our reactants. What we end with is our products. And really the only thing that sort of happens as we progress that way, essentially, is we break all the bonds on this side. And then we basically make new bonds on this side. And that's really, as we will talk about, only involving really electrons in that process. We also have that conservation of the elements as well. Again, we're not going to lose any, say, carbons along the way in that process, or say hydrogens or whatever may be there. So whatever elements that you start with in a chemical reaction, you definitely will end with the same elements on the product side. The atoms themselves are not changed in the chemical reaction, but again, just the bonds that are happening. So these are the main sort of points there of Dalton's atomic theory. Again, the two parts that sort of are not correct are, again, the idea that atoms are indestructible, and really that every atom of a particular element are identical to each other. Again, the existence of isotopes disprove that. All right, so why don't you take a second here, which what the following statements regarding Dalton's atomic theory are still believed to be true here. Okay, so let's go through it here. So we're looking for which ones are true. So elements are made up of tiny particles called atoms. That looks good. Yeah, so that is true. All atoms of a given element are identical to each other. That would be incorrect. Again, the existence of isotopes sort of disproves that. A given compound always contains the same relative numbers and types of atoms. That is correct. And atoms are indestructible, sort of incorrect. So looks like 1 and 3 here are our winners in terms of which ones are correct. So you do need to know Dalton's atomic theory, the parts of it, the ones that are correct, incorrect. Obviously, you also need to know he went bowling on Thursday, and that's really important. Any questions on that there? So Dalton's atomic theory was a good sort of starting place in terms of our ideas of about the atom. There are several laws that sort of occurred along the way as well, and some of these laws we'll actually see a little bit more when we get to say like our gas chapter here. Guy-Lussac's law measured under the same temperature and pressure that the volumes of gases reacted with one another. So his idea was under pressure and temperature, which is P1 over T1 is equal to P2 over T2. What happens in this situation at constant volume is really when this is happening. So at constant volume, what happens is as we increase the temperature, obviously, say the gas molecules would move a lot faster, causing a lot more collisions, and we would see pressure really increase. The opposite is true. If you lowered the temperature, gas molecules would fly around a lot slower, and that would result in less collisions and the pressure coming down. So the relationship of, say, something like Guy-Lussac's law is basically as you increase the temperature, you increase the pressure. And as you drop the temperature, you drop the pressure as well. We'll obviously get more into that in the gas chapter. Avogadro, he had a number. He also had a gas law, as we will learn as well. Saw that different gases contain the same number of particles. So Avogadro's law is like V1 over N1 is equal to V2 over N2. N is the moles of gas, and V is the volume. And under pressure and temperature conditions that are constant, basically as the volume increases, so there's the number of gases you have, so they sort of increase and decrease with each other, proportional to each other as one goes up. So there's the other in terms of the amount of gases you can do. These sort of gas laws also relate to the idea that you could have in stoichiometry the relationship of how many moles you have to how much volume you have in each of these cases as well, that we will see. And obviously we'll go more into detail when we get into the gas chapter about those guys. So for now, we'll kind of skip over these guys. So in terms of Dalton, as we talked about, he pictured compounds as really a collection of atoms. And here are, again, different combinations really of the same elements, nitrogen and oxygen. So we have NO, NO2, and 2O. And obviously, as you might know, as you have different sort of combinations of elements and different amounts of elements in a compound, they will have different properties depending on it. So these guys will have different properties depending on how much they are, even though they're all basically existing as basically nitrogen and oxygen coming together. They have different properties. So based on Dalton's atomic theory, there is really this understanding that the atom was the basic unit of an element that can enter into chemical combination and go through reactions. Although atoms are extremely small, it was oftentimes believed, obviously, that it did have an internal sort of structure, and that internal structure is made up of even smaller sort of particles known as subatomic particles. And those are our three big ones here. Those are our electrons, our protons, and our neutrons. As you might know, and as we will talk about here, electrons are really negatively charged particles. Protons are positively charged particles, and neutrons have no charge. So there was several sort of experiments that were done along the way to sort of understand these different types of subatomic particles. And we're going to talk about some of the experiments here. And you do need to know, obviously, some of them, we'll kind of point them out as we go through them and sort of what came out of them. It helped us understand a little bit about each of these particles and also where we find these particles in terms of the atom itself. So the first one, and a lot of experiments that were done in terms of investigation, really involved sort of the electrons. And a lot of the electron sort of investigation came out with the idea of what is sometimes referred to as the CRT, or cathode ray tube. And the cathode ray tube, as we'll see a picture there on the next slide, is really a tube that shoots these sort of negatively charged particles like electrons. And it sort of has usually electrical type plates on it, if you will. And one really important thing in terms of chemistry is the idea that basically opposites attract, right? So much like in life, they say, right, opposites attract. So things that are positively charged are attracted to things that are negatively charged, and things that have the same charge basically repel each other, right? Also, much like in life, if you get two positive people near each other, that's that's a downer. Don't want to be there. Two negative people, even more of a downer, right? So things that obviously have the same charge really don't want to be near each other, so they obviously want to get away from each other. And things with opposite charges is basically going to be attracted to each other. Pretty much through most of our chapters and stuff that we'll talk about, that's the basic connection of how a lot of molecules basically interact with each other, is basically the positive negative sort of attraction from one molecule to another is the basis, as we'll talk about, of intermolecular forces, how those molecules sort of interact with each other. So in a cathode ray tube, you got this beam of negatively charged, which is obviously going to go away from the negatively charged plate towards the positive plate. Sometimes they'll put a coating there so you can actually see it. Older TVs and computer monitors, they are CRT tubes, ones that have like the big backs. Maybe you still see them somewhere, or even big computer monitors that have the big backs, not like flat screens, obviously, or anything like that. Those are all cathode ray tube type of deals. So one of the important things in terms of really electrons and understanding electrons was done by Thomson, and Thomson did basically work with CRT tubes. And he was able to determine the charge to mass of an electron. So one of the first sort of major experiments in terms of obviously electrons and the atom itself was done by Thomson. He used these CRT tubes and he was able to do some calculations to figure out the charge to mass of an electron. And here's a picture, maybe a better drawn picture than what I did there. But again, we have our negative sort of plate, if you will, or a positive plate. So our electrons or beams of negatively charged particles would be heading in that direction as well. It is affected obviously by an electrical field. You could also affect the beams by a magnetic field, which has South Pole and North Pole, basically kind of works similar to that as well. Years ago, that's how they would fix your picture tube in your TV. They take a magnet and you could kind of adjust your picture. You don't have to do that anymore with nice fancy TVs like we have these days. So that charge to mass of an electron was found by Thomson. There he is staring at his CRT tube there. And it was found to be negative 1.76 times 10 to the 8 coulombs per gram. Coulombs is a unit of electrical charge. So that is the charge to mass of an electron. And this was a good sort of step in sort of understanding electrons, understanding sort of their behavior. The next sort of important experiment after Thomson and his work with the CRT tubes was one that was done by a guy named Milligan. And Milligan did what is sometimes referred to as the oil drop experiment. And in the oil drop experiment, much like the name implies, he basically had this chamber, if you will. He had an electrical field in there. And he basically shot droplets of oil in there. Obviously had a little spot where it could go in. And what he was able to do is, as the oil droplet would basically start dropping, it would gain a charge by friction as it started to fall. And he was able to really adjust the electrical field in this sort of chamber to a point where pretty much you could kind of just suspend the oil droplet there between the two sort of plates, if you will. And what it was able to really determine from this sort of experiments was what the charge of an electron was. So these two experiments together, the Thomson experiment where he used the CRT tube to figure out the charge to mass of an electron, and Milligan, who did this oil drop experiment to figure out the charge of an electron. If you put those together and you take something like the charge of an electron and you divide it by the charge to mass of an electron, the charges cancel and you end up with the mass of an electron. So the result of these two experiments were they're able to really calculate sort of the mass of an electron coming from these two experiments. Here's a much prettier picture than what I drew. And the charge of an electron was found here to be that number right there, minus 1.6 times 10 to the minus 9. So again, the oil droplets were sort of atomized, coming in here, coming through, and again, adjusting these charge plates, able to really suspend that oil droplet in that chamber and ultimately figure out really the charge that that electron was basically coming to get. So doing that calculation as a result of those two experiments, we get the mass of an electron, and this is the mass of an electron, 9.09 times 10 to the minus 28 grams is a mass of an electron. That is a large number, small number? That is a really super small number, right? Minus 28 means, right, we're going 28 places to the left there and putting a bunch of zeros in front of it, right? Like 27 zeros or something like that. All right, so the first thing that obviously you should know is what I just said there, that we have Thomson and his CRT tube, charge the mass of an electron, followed by Milligan's oil drop experiment, figuring out the charge of an electron, putting those together again allows us to understand the mass of an electron. Any questions on that so far? So next, we're going to talk about the proton and the nucleus. So obviously, by the early 1900s and through these sort of experiments that we were seeing, there was really two features of the atom that sort of was understood. It obviously contained electrons, which was found obviously to be negatively charged. But they also were believed to be electrically neutral, which means that if they definitely have these negatively charged electrons, they do have to have something that is positively charged, basically, to balance it out, right? In order for it to become neutral. So around the turn of the last century there, the accepted model of sort of the atom at this point was one that was proposed by Thomson. And this is sometimes referred to as the plum pudding model of the atom. And as it says there, basically thought the atom was a sphere of positive charge. So this kind of sphere of positive charge basically spread out and kind of diffused over the entire sphere. Inside the sphere, we had the electrons sort of embedded inside. And that's the idea there, pudding with raisins, basically. Raisins were like the electrons, pudding was like the positive charge that was sort of spread out over the entire thing. Also, one of the major things that he sort of did in this model was that the most of the mass of the atom was a result actually of those electrons. So this was sort of the accepted model of the atom, the plum pudding model. Basically, the sphere of positive charge, we have these electrons that are embedded inside, like we see here, and that most of the mass of the atom was made up of those electrons. So this would basically qualify for why, you know, the atom is electrically neutral. We got this nice diffusion of positive charge over it. And this was really the sort of accepted model of the atom until obviously more experiments were done. And one of the major, obviously, experiments that sort of, as we will talk about, basically move us away from this model of the atom was one that was done by Rutherford, and that is the gold foil experiment. And what Rutherford did is he basically shot alpha particles at pieces of gold foil and other metals and basically saw what happened. Now, alpha particles are pretty much, these guys are alpha particles. They are positively charged radioactive particles. They're really, the helium nucleus is really what they are. So that's really what that is. There are also, as well, in terms of radioactive particles, beta particles. And beta particles are negatively charged radioactive particles. They're really an electron. And sometimes abbreviated like that. And there's also gamma rays, which have no charge and are really just sort of pure energy. So a lot of experiments were done, and continue to be done with these types of radioactive sort of particles. They basically represent kind of like the three different subatomic particles that we have in the atom. We have like our alpha particles, which are positively charged kind of particles, our beta particles, which are like negatively charged electrons, and our gamma guys, which have no charge, which kind of like neutrons, if you want to think about it that way. So a lot of radioactive sort of particles were used a lot. So what Rutherford used was these alpha particles, which are really these sort of heavy positively charged particles. And basically what he expected to happen when he did this experiment was, as we saw there, we had basically this positively charged atom based on the plum pudding model, where we have all that positive charge. We had our electrons really embedded inside here. And what he thought was going to happen was he was going to shoot these alpha particles here. And because alpha particles are positive, and it's basically going to go through a thing of positive jelly, if you will, what he expected to happen was it should go through, but there should be a little bit of deflection, right? Because you're kind of shooting positive guys at positive guys. So he kind of expected to go through. So sort of like, this was my atom and this paper was all my positive charge, right? And if I held one side and somebody held the other side, right, and we shot like a pin at it really fast, right, it would probably pop through, right? But there'll be some deflection as it sort of bounced through that. And that's sort of what they expected to happen. They're heavy, they're moving fast. It should be able to kind of come through, but again, a little positive action should be a little bit of deflection that should occur. They were a little bit surprised that basically when they did this experiment, that's actually not what they saw. What they saw was that most of the alpha particles set up in an experiment such as this, most of the alpha particles went through pretty much undeflected. So it just went on right on through. Every so often, though, as you can see here on the sort of detection screen, our alpha particles were scattered at these kind of large angles. So they kind of bounced off of something and basically went out these large angles. They even, kind of shot back, from the source as well. So this was very sort of surprising based on the model of the atom, which was our plum pudding model, that this would happen. So seeing that most of them went through with really undeflected or only a slight deflection, and even some coming back to the source, it really had to have them sort of rethink the idea of the plum pudding model, and that maybe it's not so correct after all. Obviously, if something went through, right, and didn't get deflected or very slightly deflected, it pretty much hit nothing. Yeah, so it had no problem, right? Just kind of sailed right through. Like if I took my pen and threw it with nothing here, it should just have no problem go all the way through and stuff like that. But they did see, obviously, that as we could see here, that some of those alpha particles were scattered at really, really large angles. That meant that those positively charged alpha particles, which are moving really, really fast, had to hit something that was what type of charge? Had to hit something that was really, really densely positive, right? In order to make it moving that fast, really bounce off at those long angles. So basically what they had to do is go, well, this is probably not our right model anymore, and sort of move away from that. And really what they saw was, and thought was, all right, instead of the positive charge being spread out, sort of diffused over the entire sphere, if I then took my positive charge here and folded it, what do they say? How many times can you fold? 7, 6, 5 before you can't fold it anymore. Right. If I take all my positive charge, and now instead of it all being spread out, it's all concentrated, right, in this sort of thing, and I shoot my pen at it, right, it's going to bounce off at a really big angle like that because it hit something that was very, very positively charged. That worked pretty well. There we go. By the way, he shot alpha particles, not pens. So when you answer that question on the exam, don't write he shot pens. I usually do it with expo pens, and they go, oh, he shot expo pens at the atom, stuff like that. So they abandoned sort of this early model of the atom, the plum pudding model, and said, you know what, it's not correct. And really the sort of idea and the correct version of the atom is that the atom basically is mostly empty space. And that accounts for, again, why most of those alpha particles had no problem. They sailed right through and didn't really hit anything. They also said, obviously, for those ones that were scattered at the really large angle, the atom has a really dense positive core. And as we will later find, that's what's known as the nucleus. That is where our protons are found. And later on in like 1930s or so, that is where neutrons are found. That has no charge in our nucleus, like the 30s that was found. And electrons are traveling around the nucleus and relatively large distances from it. And another major difference between the nucleus or the model here is that most of the mass of the atom is made up of the nucleus rather than the electrons. So that was a major difference. So sort of our version here of the modern atom is we have our nucleus, which has our protons and our neutrons in it, again, later found obviously in 1930. And we have our electrons are out in that sort of empty space of the atom flying around. As you may know, and as we will talk about, electrons do not fly around in pretty little circles. They fly around randomly about the nucleus. And as we'll talk about, there's really at no given time do you know exactly where an electron is. The best you could do is say there's a high probability of finding an electron. Alpha particles, yeah. So there were alpha particles, which are basically positively charged radioactive particles. Yeah. Other questions? Is there going to be an attraction between the electrons that are flying around and the nucleus? It is, and it's back to that positive negative attraction that we've been talking about. There is an attractive force between those electrons that are flying around randomly about the nucleus and the positively charged nucleus, as it is basically positively charged. That's also, as we'll talk about when we get to bonding, why certain electrons are involved, say in bonding, and others are not, right? And depending on how close they are to the nucleus. Closer to the nucleus, they're going to be held tighter, right? Further away from the nucleus, like our valence electrons, which are the ones that are involved in bonding, are allowed to sort of leave, if you will, and be shared and stuff like that because they're not being held as tightly. So this is the major version of the atom and sort of the correct version of the atom. And obviously you should know that again, it's mostly empty space, has a nucleus that contains protons and neutrons. And most of the mass of the atom is actually that of the nucleus. This is just a table of some of the experiments that we talked about and sort of what came out of it. Obviously, you need to know Rutherford's gold foil experiment, what was done, and obviously what he thought going in terms of the atom and what came out as a result of it in terms of the atom. Any questions on that there? So we talked about it, that the idea that protons are found in the nucleus, they are positively charged. So experiments later on found that the mass of a proton was 1.67252 times 10 to the minus 24. And if you remember, our electron was like 9.09 times 10 to the minus 28 grams as our electron. And that is about 1,840 times heavier than an electron. So it was found that basically the mass of our proton much, much heavier than an electron. That also sort of makes Rutherford's idea that most of the mass of the atom is made up of the nucleus, because in the nucleus is where you find protons, and each proton is about 1,800 or so times heavier than any electron that is flying around in the atom. So at this stage, it was thought that the atom is composed of a nucleus that has most of the mass of the atom, but is actually really small in terms of its volume of the typical atom. Typical atom of the radius is about 100 picometers, and You can think of the atom as like the Superdome, if you ever been there, big football stadium in New Orleans. And like the nucleus is a small marble on like the 50-yard line. If you've ever been there, the seats are like this. You feel like you're falling out of the seat. It's so big. You stand up to go somewhere, you're like, whoa. But a really big stadium. Nucleus is just a small bit of it, but it does contain most of the mass of the atom because it has those protons and those neutrons. Protons are confined to the nucleus. Again, those electrons are traveling about at some distance. So as I mentioned before, there was always this sort of thought of, in addition to protons, that there was some other sort of particle that was found in the nucleus. And it wasn't in about 1932 that Chadwick, who did a lot of work with radioactive sort of particles, and he found that a lot of particles sort of emitted these things that resembled gamma rays, kind of these neutrals, sort of no charge sort of particles coming off. And he basically called those neutrons. And the neutron has a mass of 1.67495 times 10 to the minus 24, also about 1800 or so times heavier than any electron. Out of those three particles, are neutrons, or protons, and our electrons, it is the neutron that is the heaviest. It just barely beats out the proton. If you look back at the number there, that's why they take it to so many digits there. So it just barely beats out the proton, but they're fairly similar in terms of their mass, but the neutron actually is the heaviest, followed by the proton. And then our electron, at the minus 28 here, is going to be the lightest of all of those subatomic particles. Again, protons being positively charged, neutrons having no charge, both of those guys found in the nucleus of an atom, electrons with this negative charge flying around in that empty space of an atom. Any questions on that there? All right, so clearly you do need to know, you don't necessarily need to know the exact numbers of each of these, but you do need to know that the neutron's the heaviest, the electron's the lightest, and so forth in terms of that order. You obviously need to know the structure of an atom and what it looks like, and where we could find obviously our protons, electrons, and neutrons, and obviously those experiments that we talked about. A little bit about each of those experiments, what was done and what came out of those sort of experiments. All right, and then again, that's obviously where you can find all those particles. All right. So here is sort of a cross section, I guess, of the sort of modern nuclear atom. Again, this sort of reddish pink area is really sometimes referred to as the electron clouds by some people. That's that empty space in the atom where electrons are, again, sort of traveling randomly about. Obviously our nucleus there in the middle where we have our protons and our neutrons. All right, any questions on the atom or anything like that? All right, so now that we sort of understand how the atom is and how it came about and some of the experiments, let's talk a little about some of the features of some of the atoms. The chemistry of an atom does come from electrons. So in normal chemical reactions, it's all about those electrons, all about those bonds making and breaking. As I mentioned before, nuclear chemistry, a little bit different. Nuclear reactions different than that. And if you take 200B, there's a whole chapter on nuclear chemistry that you'll talk about. But there are involved, obviously, electrons in normal basic chemical reaction, combining to form different properties when these elements come together. And clearly, when we do form different compounds, they are very different than the elements that make them up. You have something like sodium chloride. That is obviously salt, for example, right? And that's very different than the two elements that make it up, like sodium metal, which is a soft metal, and chlorine gas, which is a green toxic gas. So through the magic of chemistry, right, they come together and we could throw some salt on our fries and not die, right, when we do that. So things have very different properties, obviously, than the compounds that they come from. Same thing with water, right? Water is basically hydrogen gas, oxygen gas, which has very, very different properties, obviously, than water itself in its sort of liquid state. So let's talk about some of these properties of atoms, and that's going to be the atomic number, the mass number, and what isotopes are. So we're going to start with the idea of isotopes, and isotopes are really the same element, but it has different masses. So atoms that are isotopes have the same number of protons, but they have a different number of neutrons, and that's what gives it the mass that's different. That also is what sort of violates, if you will, Dalton's atomic theory there, that they're all identical to each other, is the existence of these guys. They do show identical chemical properties, and again, that's because basically it's all about electrons. So as long as you don't touch what's in the nucleus, you know, nothing will change. So two isotopes, for example, here of sodium, that's sodium 23 and sodium 24 there. And the difference is the number of neutrons. They both have 11 protons. So the protons is really the most important in terms of what element you're dealing with. The number of protons tells you the element that you're dealing with. That is, as we will talk about, basically the atomic number of a atom. So if you know how many protons there is, you should know what element it is, and that is the one that basically determines what element it is. That's why having different neutrons will not affect the element. It's basically the same element as well. So that number of protons is the atomic number, and the atomic number is sometimes abbreviated with a Z. And the definition of the atomic number is the number of protons there are in an atom. Now, if you have a neutral atom, which means it has no charge, then the number of protons should equal the number of electrons, as each atom pretty much has those three particles: protons, electrons, and neutrons. Protons being positively charged, electrons being negatively charged, and obviously neutrons having no charge. So the atomic number will also tell you in a neutral atom the number of electrons. It's really important to note that the definition of atomic number. So if you're asked what is the definition of the atomic number, the definition of the atomic number is just the number of protons. So that is the definition of the atomic number. Second to that is, again, if it's neutral, it will actually tell you, again, how many electrons that you have. We can find the atomic number on the periodic table, and that is the number above the element symbol. So like lithium is 3. That would be the atomic number. Hydrogen is 1. So the number typically on the periodic table above the symbol is the atomic number. And if you look at the periodic table, there is no element that repeats the atomic number. So every single element has its own atomic number, which is what we were just talking about a second ago. Pretty much if you know the atomic number, which is the number of protons, you know what element it is. So every element will have the same one. So for example, fluorine, which if you look up there on the periodic table is number 9. A neutral fluorine atom should have 9 protons, which are positively charged, should also have 9 electrons, which are negatively charged, which has no charge overall when you put it together. Same thing with nitrogen. If you look up there on the periodic table, nitrogen is number 7. And again, that means that our neutral nitrogen should have 7 protons and 7 electrons, again, giving you no charge when it's all said and done. You will never find a nitrogen with 5 protons, because somebody with 5 protons is boron. Yeah. So again, if you change the number of protons, you change what element it is. And that does not happen in normal chemical reactions. Again, in nuclear reactions, that's pretty much all that happens, is that there's things in the protons get changed, the neutrons get changed. So that's why we don't have conservation of elements in nuclear reactions. But in chemical reactions, like we talked about in this chapter, that never happens, because it's all about the electrons. So we do have that conservation of it. Another important number is the mass number. And the mass number is sometimes abbreviated A. And that is the total number of protons and neutrons there are in an atom. And that's important because if you kind of put the mass number and the atomic number together, where the mass number is our protons plus our neutrons, and our atomic number is our protons, and you subtract those, you're left with the number of neutrons. So if you take the mass number minus the atomic number, that will tell you how many neutrons there are in an atom. Except for hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron. All other elements have all 3 particles. So hydrogen is an exception to that, which is why hydrogen has some interesting properties that we deal with, and why sometimes hydrogen is found on both sides of the periodic table. They used to put it on. But hydrogen, proton, electron, no neutrons, but everybody else has all three of those things. When you calculate or ask to give the atomic number, the mass number, the number of protons, electrons, and neutrons, they all should be positive whole numbers. So all those things should be positive whole numbers: protons, electrons, neutrons, atomic number, mass number. Can I find the mass number on the periodic table? So like I go to hydrogen, it says 1 and this says 1.008. Is this number the mass number? The answer is no, it is not the mass number. This number on the bottom is the atomic number, not atomic mass. I'll say that right. That is the atomic mass, not the mass number. One way to remember that is what the last thing says there. They all need to be positive whole numbers. So if you look on the periodic table, pretty much none of those numbers on the bottom are whole numbers. They're pretty much all decimal numbers. So don't be the person that writes the decimal number on the exam. Yeah. And so I would come up and ask, should I use the number that's on the periodic table for that? I'm going to probably say you should not do that, maybe, or you should think about it. So only the atomic number can be found on the periodic table. Mass number is not found on the periodic table. What confuses a lot of people is sometimes the mass number and the number you see on the periodic table are very close to each other, but they should be whole numbers, and you should have enough information in these type of problems to figure out the mass number, atomic number, protons, electrons, and neutrons based on the information given to you. Any questions on that there? So isotopes, as I mentioned earlier, are the same element, but they do have different numbers of neutrons, which gives them their different sort of properties and characteristics. So for example, if we look at hydrogen, hydrogen has 1 proton, 0 neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. Tritium, which is like the radioactive version of hydrogen, has 1 proton and 2 neutrons. Isotopes have the same atomic number, but different mass numbers are known as isotopes. There are a couple of ways that we write isotopes in terms of their formulas, and this is the one very common way, which is what we see here. We use the symbol, and on the top left of the symbol is the mass number. Bottom left of the symbol there is the atomic number is written. Another way that sometimes isotopes are written is they will do the symbol dash a number, and that number is typically the mass number. So for example, sometimes people will write something like Cu64, and that is copper 64, isotope copper, and that 64 is the mass number. So if we were to write it in the other way, 64 would go up on top. If I needed the atomic number, I just go to the periodic table and I find copper. And if I find copper over there, getting old to see that periodic table, they should make it bigger. I don't know. But I think it's a 29 still. I hope they haven't changed it. And that would be the atomic number that you have there. And that would be one way that you would write it. Clearly here, if I want to know how many neutrons, top number minus bottom number, right, is how you get to the number of neutrons, which is our mass number. So if we were to write our symbols for our hydrogen sort of isotopes, we would do 1 proton. If you weren't sure, you'd go to periodic table, look up number 1, and you would see that the symbol there is hydrogen, or H. And we should put 1 on the bottom, which is our number of protons, or our atomic number. Our mass number would be protons plus neutrons, which in this case is 1 plus 0, which is 1 as well. So that would be the way that you would write the symbol for hydrogen. Now, even if you saw deuterium here and wasn't sure it was hydrogen, but they told you it had 1 proton, that would tell you that the atomic number is still 1, which means you would go to the periodic table and number 1 would still be hydrogen. And it would still be 1 for the atomic number. You would then add these guys together. 1 plus 1 gives you 2, which would be our mass number that should go up on top. And that would be deuterium. Again, here, even though it doesn't say hydrogen, it says tritium. If you see the 1 proton, still atomic number 1, which means hydrogen should be the symbol. And again, here, 1 plus 2 gives us 3. 3 would be there. So these are all 3 of the symbols for hydrogen, deuterium, and tritium. They're all hydrogen, as you can see, because they basically all contain still one proton. They also have very different properties because of those neutrons as well. One being radioactive, one being not so radioactive on the other side there. Any questions on that there? Yeah. All right, so I want you to try these here. So for each of these, the number of protons, electrons, and neutrons for each of these guys. See what you come up with. All right, let's take a look. So we'll start here with the first one. That is cobalt CO. So again here, the top number going to be our mass number. Our bottom number here going to be our atomic number. So our atomic number does tell us the number of protons. So in this case, our number of protons should be 27. We also know that there is no charge, because if there was one, it would be written right about there. So you could assume that it is neutral. And because you could assume that it's neutral, that makes the electrons fairly easy. We need to have a balancing number of negatively charged electrons, right? That gives us 27, which pretty much gives us that no charge is happening in this case. Here to find our number of neutrons, that is going to be, again, our mass number minus our atomic number. And that is going to be, in this case, 60 minus 27. That looks like perhaps a 33, I think, in that case. Any questions on that one there? Coming here to Cl, which is chlorine, looking at our atomic number first on the bottom. That means we do have 17 protons. Again, nothing written here, so we could assume that it is neutral. So we would have a matching number of negatively charged electrons. And for our neutrons, taking our mass number, which is our top number, 37, minus 17 looks like a 20 in that case. And lastly here, that's uranium, I think, and that is a 92 for our protons. Again, no charge, so matching number of electrons to give us that no charge. And our neutrons going to be a 238 minus a 92. That's a big number, like a $1.46, something like that, maybe, I think. Yeah. Yeah, we'll talk about things with charge in just a second, what happens with those. Yeah. Other questions? Okay. All right, then let's do this one's here. So write the symbol with the mass number and atomic number for each of these guys and see what you come up with. Okay, let's take a look. C, so we'll start with krypton, which is Kr. And if we go there to the periodic table, I think krypton should say 36, I hope. That is going to be its atomic number that we could get. And that will go bottom left. Our mass number is our protons, which would be 36 in this case, and our neutrons together. So that's going to be 36 plus 48 gets us an 84. And we should go up on top on that one there. Any questions on that there? Nitrogen is N on the periodic table. Again, if we go to nitrogen there, that is going to be 7, which would be its atomic number. And that would go on the bottom. Once again, to get our mass number, we're going to add our 6 plus our 7 there, going to get us 13, I believe, as our mass number in this case. And lastly, here we're looking for iron. Iron is Fe on the periodic table. And if you go up to iron there, that is 26, I believe. And that would be on the bottom here. They actually gave us our mass number of 56. That means in this case, we have, in terms of protons, would be 26. This guy is neutral charge, so we would have a matching number of electrons. And our number of neutrons would be our mass number of 56 minus 26, giving us 30 in this case, yes. Any questions on any of those things? Write in the symbols with the mass number, atomic number. You do need to be able, obviously, to do all those things. Mass number, atomic number, protons, electrons, and neutrons. Now, to answer the question that was asked earlier, if things do have charges, what really sort of changes? When something does have a charge, that is what is referred to as a ion, are things that have charges, charged entities. And there's really two types of ions that we'll come across, and that is our cation. And cations are positively charged ions. And there's also anions, which are negatively charged ions, basically. So for example, here, we'll just borrow these two on this slide. If we had and if we look at our nitrogen, for example, to start with, our nitrogen here has, in terms of our protons, it's got 7 protons. In terms of our electrons, because it's neutral, it also has 7 electrons. And then our neutrons there, 13 minus 7, which gives us our 6. Now, if we have the same sort of guy here, but it carried a -3 charge, which is typically what nitrogen will sort of carry, what's going to change in this case? So we can still know that it is nitrogen. We cannot change the number of protons, because as we talked about, if we change the number of protons, it's no longer going to be nitrogen, right? So the atomic number's got to stick, which means the number of protons has to be the same. And that is why it is the same here in this case. The number of protons in this case would be 7. The number of neutrons in this particular example would still be the same. It would still be 13 minus 7, which is 6. So it really is the electrons that change when something gains a charge. And in this case, the number of electrons would be how many? Would be 10 electrons, right? 10 negatives, right? And 7 positives leaves you a -3 left over, which is, again, where that -3 sort of charge comes from in this particular case. Same thing if you had something that was, say, positively charged. Say this iron here had a +2 charge. Again, because it is still iron, it's got to still have the 26 protons. It will still, in this case, have 56 minus 26, which is 30 neutrons. Again, here it is the electrons that would change in this case. And in terms of electrons, it would have 24 electrons. Yeah. 26 positive guys, 24 negative guys, leaves you a +2 left over in terms of the charge because of the extra couple of protons that it has. And that is where the charge comes from. So when something gains a charge and becomes an ion, either a cation or an anion, it is only the electrons that change based off of that. And what we see if we compare our anion here, our negatively charged guy, to our neutral guy, it actually gained 3 electrons. So anions results from gaining electrons. And that is basically what the charge tells you. If you see a negative charge, it means it has gained electrons. It has more electrons than protons. And the actual number of the charge tells you how many it gained from the neutral element, basically. Same thing here. If we compare our positive guy to our guy that has no charge, the difference here is the number of electrons has decreased or has lost a number of electrons. And that's what happens in a cation. You basically will lose electrons. And the same thing here, the positive tells you that it's lost electrons. The number tells you how many electrons it lost from the neutral guy. Any questions on that there? So why don't you do this one here? Let's do chromium 54. And let's say it has a +3 charge. Chromium is 24 there. And why don't you do there. All right, how many protons, electrons, and neutrons did each of those guys have there on the bottom? Okay, let's take a look. So here we'll start with our chromium. So we got our atomic number there, which is 24. So that will give us our protons. Our neutrons will take our mass number, which is the top number, minus our atomic number, which is the bottom. And that looks like a 30, I think. And our number of electrons here, which should change. So basically, this tells us that we have a positive charge, so we lost electrons, and we lost 3 electrons. So the easy way, if you want to remember, is obviously protons and electrons would be equal to each other, right, if it was neutral. So if you lost 3 electrons, take 24 minus 3 is 21, right? In this case, that gives you a +3 left over, which again is our charge. And again, where that comes from. Any questions on that one there? Same thing here. We got 9 for our protons, as that's our atomic number. Our neutrons here would be 19 mass number minus atomic number, which would be 10. And in this case, we have a -1 charge. Again, negative means that it gained electrons. So again, if it was neutral, we would have 9 electrons, but in this case, since it actually gained 1 electron, we add 1 more, gives us 10 electrons, right? Gives us our -1 left over in this case. Yeah. Any questions on what to do if it has a charge? All right, so obviously you need to be able to do that as well. All right, so to finish up this sort of chapter here, we're just going to briefly talk a little bit about energy. Again, we don't do too much with energy in this class, but it does pop up because they assume you did like chapter 6 along your way here in your journey. Energy is the ability to work or produce heat. Work is a force is acted out over a distance. When we talk about heat, heat is sometimes abbreviated, and you might have saw this in your previous class. Q is heat, sometimes the representation of it, and a lot of times we could calculate a lot of times heat through the specific heat equation, which is maybe this one that you might remember. Q is equal to ms delta T, M being mass, S being the specific heat capacity, and delta T is the change in temperature. So that's one thing that you could do really simply with, say, a thermometer and a coffee cups, and figure out how much heat's being given off in a reaction by looking at really water. The law of conservation of energy, as we've talked about, we don't create nor destroy energy, but it can be transformed from one form to the next. Total amount of the energy content in the universe is constant. So one way to think about energy and sort of the transfer of energy is you could kind of think of it as sort of a perfect sort of transfer, if you will. And what I mean by that is, again, if something should give off a certain amount of energy, again, there has to be something that will accept that basically same amount of energy. I think I dropped my keys the other day, right? And that's sort of that idea of what happens. There's different types of energy, obviously. And these are just some of the sort of energy that we see. There's radiant energy that comes from the sun. There's thermal energy that's associated with the random motion of atoms and molecules. Thermal energy and temperature are different from each other. Temperature is a measure of sort of the amount of energy in that particular sort of instance. Thermal energy is really based on the amount of molecules and atoms that are present, how much motion that you have. So a classic example of that, for example, is if you have, say, a bathtub at 40 degrees and it has like a coffee cup at like 90 degrees, the bathtub actually has more thermal energy than the coffee cup, because way more molecules and atoms in the bathtub than there is in the coffee cup. Coffee cup has a higher temperature because it's a much smaller place, right? Much smaller volume. So the amount of energy generated in that smallest area is going to cause a greater sort of change in temperature. It takes a lot more energy to raise the temperature, say, of a bathtub of water than it does, say, a small coffee cup that's basically water as well, right? And that has to do with, for example, that specific heat equation. Specific heat of water is 4.184 joules per gram per degree Celsius. So it takes that much energy, which is a big number, to change the temperature and stuff like that. So there are sort of different temperature and thermal energy. Chemical energy, there's energy stored within bonds. When we make bonds, is that endothermic or exothermic when we make bonds? Does energy need to be released or absorbed when we make bonds? Actually, it has to be released, yeah? So in order to make a bond, everybody's moving around a lot, right? So as they release their energy, they slow down. and they can come together, right, to make the bond. So making bonds is sort of an exothermic sort of process. When we break a bond, they're together, which means when you put energy into them, they gain energy and they have enough to wiggle away from each other. Exactly how that happens, by the way. So they gain all that energy, they're able to sort of escape each other. So actually breaking a bonds is an endothermic sort of process, and making bonds is sort of exothermic, which is releasing energy. Nuclear energy, there's energy stored within the collection of neutrons and protons, and most nuclear reactions involve what's in the nucleus: protons, protons and neutrons, converting protons to neutrons, neutrons to protons. That takes an enormous amount of energy to do so, which is why nuclear reactions like fission reactions typically release a lot of energy as a byproduct of that. Potential energy, again, is that classic example, right, of, the position, the big giant boulder on the hill that's about ready to fall down. Hopefully there's nobody down here. And again, obviously, if it falls over, it can convert to kinetic energy. When it hits on the bottom, it will obviously transfer that energy to hopefully nobody underneath it. So kinetic energy is really the energy due to motion, and we're not going to obviously do any type of kinetic energy sort of calculations. But there are some common units of energy, which is sort of important, and joules is a very common unit of energy, and kilojoules is another very common unit, and that's joules. Joules, there you go. These are two common units. There are 1,000 joules and 1 kilojoule. Also, calories, lowercase c, and kilocalories are also very common units of energy. I say lowercase c because capital C is nutritional calories, right? And that's 1,000 of the little guys, the little calories there. And the same relationship, 1,000 calories is 1 kilocalorie. And the relationship between joules and calories, 4.184 joules is equal to 1 calorie, just like the specific heat of water. Something that we will see is this relationship along the way, and that is that a joule is equal to a kilogram meter squared second squared. So in our application where we'll see this, you sometimes need to make sure that you convert the mass into kilograms to get it to joules. So that is a relationship that we do see in our sort of section here. So as I mentioned before, there are some of our units. Joules equal to 1 Newton meter, which we don't use too much here. But again, this relationship we do see. A calorie's definition is really the energy required to change 1 gram of water by 1 degree Celsius. It's really kind of similar to the specific heat capacity definition, which is 1 gram of a substance by 1 degree Celsius. Nutritional calories is sometimes abbreviated with a capital C. And again, one of those is 1,000 of the little guys with a little c. And that's the same as 1 kilocalorie, right? So we do come across some of these sort of conversions along the way. Again, they assume that you probably did that chapter in the order of the book, but we kind of skip it in this class. Any question on energy there? All right, that wraps up chapter 1.